In this second screencast of 2, we're going to look at solving systems of linear equations using analytic methods, namely substitution and elimination. So let's look at our first means of solving systems of equations using analytic approaches. It's called the substitution method. So substitution method is a 3-step process. First, we're going to try to solve one equation for one of the variables. When we've done that, we're going to then take that, which is now an equation with just one variable in it instead of 2, and substitute that expression into the other equation to replace that variable. Having done that, we will solve the other equation. Once we've solved that, we actually have one of the two coordinates in our solution. We have to go back to the other equation and solve for the other variable once we've done that with the first equation. And that gives us a point, which is the intersection of this system. Let's look at an example step by step here. We'll go in slow motion. So let's take the system of linear equations 2x minus y equals 10 and 8x plus 2y equals 16. So this is a good candidate for the substitution method because it's already got one of the equations having one variable almost isolated. It has a coefficient of -1 instead of 1, but it's really, really close. So we're going to do step 1, which is to solve one of the equations for one of the variables. Now, the first equation here is much easier to work with, somewhat easier to work with because the y is almost by itself. So we're going to add the y to the other side, and then we're going to subtract 10. There are multiple ways of doing this, but this is just one of them. And we're going to subtract 10 from both sides to get the y on one side and everything else on the other. And just flipped around, that becomes y equals 2x minus 10. Algebraically equivalent to this first equation. But now we know that y and 2x minus 10 are the same thing. And so we can substitute in 2x minus 10 anywhere we see a y. Indeed, that is the next step. We're going to take this 2x minus 10, and this is the key to the substitution method. Since 2x minus 10 and y are interchangeable, they are the same thing. Wherever we see a y, and there's a y right here in the second equation, we can substitute in a 2x minus 10. And so this equation then becomes 8x plus 2 times quantity 2x minus 10, which is the same as y, equals 16. So we now need to solve for this because we have one equation and one variable. So we get 8x plus 4x minus 20 once we've distributed that 2 equals 16. We'll combine our like terms of 8x and 4x, and we get 12x minus 20 equals 16. And so from there, we're really just 2 steps away from understanding what x is. We're going to use the addition property of equality, add 20 to both sides, which gives us 12x equals 36. Now we're going to use the division property of equality to isolate the x, dividing everything by 12 on both sides, which cancels out the 12 because 12 divided by 12 is 1. We get x equals 3. Now we're not done, but that is half of the solution to this system. So the final step, once you've identified one of the two variables, is to substitute that value into the other equation. Now, we have already solved for the other variable, so it's y equals 2x minus 10. We're going to take y equals 2x minus 10, and we're now going to substitute in x equals 3 into that because we know that our solution occurs where x equals 3. And so if we put x equals 3 into that, we get y minus 2 times 3 minus 10. Using our order of operations, that becomes 6 minus 10, or -4. So now that we know the x and the y coordinates, we now know the solution to this system is the point 3, -4. Now in these screencasts, for condensing for time, I often skip a very important step of checking your solution. You should take that point 3, -4 and make sure it works in both equations in the system. In other words, plug in the 3 for x and the -4 for y, and you should get a true statement. Let's look at the second major analytic method for solving linear systems, and that is called the elimination method, sometimes called the addition or subtraction method, but elimination is what we're going to use. So step 1 is to multiply one or, in some cases, both equations by a number to result in two equations that contain opposite terms. The idea here is we're going to multiply one or more of the equations by numbers, constants, to be able to cancel out a variable right away through addition. That second step is to add those two equations, and that will eliminate one variable. We'll then solve the equation and have one of the variables solved for. From there on, it runs very similar to the substitution method. You're going to take that variable that you now know, substitute into the other equation to solve for the other variable, and then you have the set of coordinate points, x and y, that are the solution to your system. So let's look at an example. Let's take x plus 2y equals 10 and x plus y equals 6. This is a classic candidate for the elimination method. What we're looking for is a number to multiply one or both the equations by, such that when we add the two equations together, one of the variables is going to cancel each other out. So you could multiply the bottom equation by -2 and the y's would cancel out, but even simpler in this particular case is to multiply the bottom equation by -1, which will result in an x and a -x, which when we add them, they're going to cancel each other out. Okay, so now we're going to go ahead and add those equations together. So it's very important, and this is a very common mistake in the elimination method, not multiplying every term in the equation on both sides by the same constant. So if we choose -1 here, we're going to multiply -1 by the x, -1 by the y through distribution, and what we do to one side in algebra, we must do to the other to keep it an equation, and we're going to multiply the 6 by -1. So we wind up with, when we distribute, -x minus y equals -6 in the second equation. So now what we're going to do is add those equations together, and you notice x minus x cancels out the x's. 2y minus y is equal to y, and 10 minus 6 is equal to 4. If you haven't canceled out one of the variables when you do this, something's wrong. Our final step will be to take that value for y and substitute it into one of our equations to solve for the other variable. You can use either one. I just chose you as the first. X plus 2y equals 10. We now know that y equals 4, so we're going to substitute in a 4 for y. We get x plus 2 times 4 equals 10. We're going to subtract that 8 from both sides, and that's going to give us x equals 10 minus 8, or x equals 2. So I got the x and y coordinates for the solution to my system of equations. The solution is 2, 4. I'm going to wrap this screencast up with the discussion of what the solutions actually look like when you graph them and when you solve them. So your typical situation is going to be a set of lines that do intersect as a system, and there's one solution. What that looks like is you're going to get an answer for A, you're going to get an answer for B. That's going to be the coordinates of that point where they intersect. Let's call it A comma B. That is called a consistent and independent system. It's consistent because there is a solution. It's independent because there's only one solution. The second category of systems comes when they are the same line. Fairly rare. Usually one is a multiple of the other. What you're going to get as a solution, if you ever solve this using an analytic method, is going to be an infinite set of points along the same line. You're going to get something like 3 equals 3 or -5 equals -5. It's going to be a true statement, meaning that the two lines are actually the same line. And every set of points on the line, the entire set of points on the line, is the solution. The final set of possibilities when we're dealing with two linear equations in a system is the two lines are parallel to each other. Graphically, it looks something like this. As you can see, they are never going to intersect each other. There is no solution. The solution is the empty set, or does not exist. What this looks like when you solve it analytically is something like 5 equals 4 or 0 equals 3. If you get a false statement like that, that's an indication that analytically it is this inconsistent system. So an inconsistent system has no solution. I should have mentioned that second system is both consistent because it has solutions and dependent because it has infinitely many solutions along that line. So those are the three possibilities with linear systems in terms of their solution or lack thereof. So here we focused on solving systems of equations using analytic methods of substitution and elimination.